Hi, my name is Andres, and this is my Lab 11. I chose to study a golf ball pendulum. I found a video online, and the main problem was to model the pendulum motion through velocity and tension force. My results were that velocity and tension force are greatest at the bottom of the swing and are least at the top parts of the swing. They are both reduced by dampening effects, however. This is the video that I found from the internet, and I have it here on tracker. The calibration stick measures the diameter of a golf ball, which I simply looked up online. I chose the origin to be arbitrary and the positive x-axis to be oriented to the right. And here I tracked its position throughout for a short time frame. And I copied this position data to an Excel file, which I later used in my Python code, which you'll see. So the relevant models are the momentum principle, dp/dt equals F net, and the energy principle, the change in energy is equal to work done by the surroundings. Other relevant equations are F net perpendicular to the motion equals dp/dt perpendicular, which is itself equal to the magnitude of momentum times the rate of change of direction of momentum, which is also equal to the mass times the velocity squared divided by the radius of the kissing circle, which we'll see is simply the length of the rope. F net parallel is equal to dp/dt parallel, which is equal to the rate of change of magnitude of momentum times the unit vector of momentum. Kinetic energy is half mass times velocity squared. Change in potential energy due to gravity on Earth is equal to mass times g times the change in height, and the period of a pendulum is equal to 2 pi times the square root of the length divided by g. Here I have the code. I imported the data. I have the mass here. It says star because I used the other code, but it's obviously of the golf ball, which is 0.04593 kilograms. I have delta t equals to 0.1 seconds. Here I'm calculating velocity from my data, and then momentum from the data, and have the calculations of F net parallel perpendicular using what you already saw just a little bit ago. And I have a black arrow modeling the tension force, which is just F net minus the force due to gravity, and of course F net in red. So we'll run this. There it is. It's very jerky because I have little points for the position data, so it's obviously a rough approximation. To find the radius of the kissing circle, I needed to find the length of the rope, and the period of a pendulum is equal to 2 pi times the square root of length divided by gravity. So using this equation and using the period through tracker, which is just the difference in peaks in seconds, I found that to be 1.2. I was able to measure L, the length, to be 0.3578 meters. F net perpendicular is equal to the force due to tension, which is of course always perpendicular to the motion, plus the force due to gravity, the component that is perpendicular to the motion, which is itself equal to mass times velocity squared divided by L, the length. So that the force of tension minus mg times cos theta is equal to mv squared divided by L, and theta is seen here. So you can see that's the perpendicular component of gravity. Rearranging this, you get force of tension is equal to mg times cos of theta plus mv squared over L. The minimum velocity is at the top of the swing and the max velocity is at the bottom of the swing. You are easily able to tell this just through not only intuition, but the fact that these waves, the slope is greatest here mid-swing, so therefore the velocity is greatest mid-swing, and the velocity is 0 at the change of direction at the top of the swing. Since the force of tension we established to be that equation, there is a minimum force of tension at the top of the swing because velocity is 0, and maximum force at the bottom of the swing when cos of theta reaches its max value of 1 and velocity is also greatest. So then at the top I calculated the force due to tension. I plugged in 0 for velocity, and I approximated theta, the angle, to be about 20 degrees, and I got a value of 0.423 newtons. And now using the energy principle for the bottom of the swing to find the velocity, I have delta E equals work. With the system of the ball plus earth, work is equal to 0. There are no external forces acting on it, which you get kinetic energy final minus kinetic energy initial plus potential energy due to gravity equaling 0, assuming there's no change in internal energy. At the top of the swing, initial, which is initial kinetic energy, it's equal to 0 because velocity is 0. So then this equation comes out to be 0.5 mv squared plus mg dh, delta height, which I calculated because height final being 0 and height initial being L minus L cos of 20 degrees. So velocity turned out to be 0.651 meters per second. And I actually calculated the tracker velocity by taking the slope mid swing and found velocity to be 0.662, which is a rather good agreement for such rough approximations. Plugging this into the equation we found earlier, where this time velocity is 0.651 and theta is 0 degrees, the force due to tension turned out to be 0.505 newtons, greater as we would expect it to be. If we include dampening effects of air resistance and friction, internal energy of the system increases because of vibration, heat, and sound, etc. So delta E internal is a positive number. Therefore, instead of having velocity squared equal to negative 2 gdh, we have velocity squared equal to this minus dE internal. So it's clear that velocity at the bottom will be less with dampening, and thus the tension force of the rope will also be less with dampening. Thank you.